Hello, good day. Welcome to our third thermodynamics lecture video. Today, we will discuss about thermodynamics basic concepts, and it is essential to familiarize these concepts to understand its behavior and mechanism. Studying these concepts can also avoid confusion and possible misunderstandings in the future. Let's start with a definition and illustration of systems. A system is defined as a quantity of matter or a region in space chosen for study. Take for instance, let's consider this figure as our system. A system can be closed or open, and the mass or region outside the system is called surroundings. And this thin or the real or imaginary surface that separates the system from its surroundings is called the boundary. The boundary of a system can be fixed or movable. Note that the boundary is the contact surface shared by both the system and the surroundings. Mathematically speaking, the boundary has zero thickness, and thus it can neither contain any mass nor occupy any volume in space. As what I have said from the previous slide, a system can be closed or open. And let's discuss first what is a closed system. A closed system, also known as a control mass, consists of a fixed amount of mass, meaning your mass is constant, and no mass can cross its boundary. That is, no mass can enter or leave a closed system. But energy in the form of heat or work can cross the boundary, and the volume of a closed system does not have to be fixed. In special case, when there is no mass and no energy can cross the boundary, then it is called an isolated system. Consider the piston cylinder device as shown in the figure. Let us say that we would like to find out what happens to the enclosed gas when it is heated. Since we are focusing our attention on the gas, it is considered as our system. The inner surface of the piston and the cylinder form the boundary. And in this case, this is a moving boundary and this one is the fixed boundary. And since no mass is crossing this boundary, it is considered as a closed system. Notice that energy may cross the boundary and part of the boundary, the inner surface of the piston, may move. Everything outside the gas, including the piston and the cylinder, is the surroundings. How about the open system? An open system or a controlled volume is a properly selected region in space. It usually encloses a device that involves mass flow, such as compressor, turbine, or nozzle. The flow through these devices is best studied by selecting the region within the device as the control volume instead of as control masses or closed systems. Both mass and energy can cross the boundary of a control volume. The boundaries of a control volume are control surfaces, and they can be real or imaginary. In the case of a nozzle, the inner surface of the nozzle forms the real part of the boundary, and the entrance and exit areas form the imaginary part, since there are no physical surfaces. A control volume can be fixed in size and shape, as in the case of a nozzle, or it may involve a moving boundary as shown in this figure. Although most control volumes have fixed boundaries and do not involve any moving boundaries, a control volume can also involve heat and work interactions just as a closed system, in addition to mass interaction. Let us consider the water heater in the figure. And now, we would like to determine how much heat we must transfer to the water in the tank in order to supply a steady stream of hot water. Since hot water will leave the tank and be replaced by cold water, it is not convenient to choose a fixed mass as our system for the analysis. Instead, we can concentrate our attention on the volume formed by the interior surface, or this is called the control surface of the tank, and consider the hot and cold water streams as mass leaving and entering the control volume. Now let's tackle the properties of a system. Any characteristic of a system is called a property. Few examples of these properties are pressure, temperature, volume, mass, viscosity, and thermal conductivity. Properties are considered to be either intensive or extensive. When you say intensive property, these are the values independent of the mass of a system, and the examples for this are the temperature, pressure, and density. While the extensive property are the values that depend on the size or extent of the system. And the example for this are the total mass, total volume, and total momentum. An easy way to determine whether a property is intensive or extensive is to divide the system into two equal parts with an imaginary partition as shown in the figure. Each part will have the same value of intensive properties as the original system, but half the value of the extensive properties. And these extensive properties per unit mass are called specific properties. And some examples of specific properties are the specific volume, which is given by nu is equal to V over m, and the specific total energy E is equal to energy over m. Another concept to learn is about continuum. Matter is made up of atoms that are widely spaced in the gas phase. Yet, it is very convenient to disregard the atomic nature of a substance and view it as a continuous, homogeneous matter with no holes, and that is considered as continuum. The continuum idealization allows us to treat properties as point functions and to assume that the properties vary continually in space with no jump discontinuities. This idealization is valid as long as the size of the system we deal with is large relative to the space between the molecules as shown in the first figure. The length scale associated with most flows, such as seagulls in flight, is in orders of magnitude larger than the mean free path of the air molecules. And also, in this figure, there are about 2.5 times 10 to the 16 molecules of oxygen in the tiny volume of 1 cubic meter at 1 atmospheric pressure at 20 degrees Celsius. The continuum model is applicable as long as the characteristic length of the system, such as its diameter, is much larger than the mean free path of the molecules. And despite the large gaps between molecules, a substance can be treated as a continuum because of the very large number of molecules, even in an extremely small volume. And this continuum idealization is implicit in many statements we make, such as the density of water in a glass is the same as at any point. Now, let's talk about another terminology often used in this course. Density is defined as mass per unit volume, and it is denoted by ρ, and the SI unit is kilogram per cubic meter. This is how to illustrate the density. These two objects are equal in volume but different in mass due to their density. So this is considered as high density because it has more massive mass, and this one is low density because it has lesser mass. The density of a substance in general depends on temperature and pressure. The density of most gases is proportional to pressure and inversely proportional to temperature. Liquids and solids, on the other hand, are essentially incompressible substances, and the variation of their density with pressure is usually negligible. The reciprocal of density is the specific volume nu, which is defined as volume per unit mass. The SI unit is cubic meter per kilogram. Sometimes, the density of a substance is given relative to the density of a well-known substance. This is called as specific gravity, or SG, or relative density, and it is defined as the ratio of the density of a substance to the density of some standard substance at a specified temperature. Usually, this substance is water at 4 degrees Celsius, for which density is equal to 1,000 kg per cubic meter. Note that the specific gravity of a substance is a dimensionless quantity. However, in SI units, the numerical value of the specific gravity of a substance is exactly equal to its density in grams per cubic centimeter or kilogram per liter. The specific gravities of some substances at 20 degrees Celsius, or at 0 degrees Celsius, is given by this table. Note that the substances with specific gravities less than 1 are lighter than water, and thus they would float on water if immiscible. So in this case, since oil has lower density or less dense compared to water, oil floats at the top of the water. And the weight of a unit volume of a substance is called specific weight or weight density, and it is expressed as gamma equals to density times the acceleration due to gravity. Let's define what is state and equilibrium. Consider a system not undergoing any change. At this point, all the properties can be measured or calculated throughout the entire system, which gives us a set of properties that completely describes the condition or the state of the system. Meaning, the state is a condition of a system. At a given state, all the properties of a system have fixed values. If the value of even one property changes, the state will change to a different one. In the first figure, it shows a system at two different states. It has the same mass and temperature, but their volume is different. Thermodynamics deals with equilibrium states. The word equilibrium implies a state of balance. A system in equilibrium experiences no changes when it is isolated from its surroundings. And there are many types of equilibrium, and a system is not in thermodynamic equilibrium unless the conditions of all the relevant types of equilibrium are satisfied. For example, a system is in thermal equilibrium if the temperature is the same throughout the entire system, as shown in this figure. Initially, the temperature is not balanced, but eventually it will reach thermal equilibrium, or it has the same temperature for the entire system. While mechanical equilibrium is related to pressure, and a system is in mechanical equilibrium if there is no change in pressure at any point of the system with time. However, the pressure may vary within the system with elevation as a result of gravitational effects. And if a system involves two phases, it is in phase equilibrium, when the mass of each phase reaches an equilibrium level and stays there. Finally, a system is in chemical equilibrium if its chemical composition does not change with time. That is, no chemical reactions occur. As noted earlier, the state of a system is described by its properties. But we know from experience that we do not need to specify all the properties in order to fix a state. The state postulate requires that the two properties specified be independent to fix the state. The state of a simple compressible system is completely specified by two independent intensive properties. Two properties are independent if one property can be varied while the other one is held constant. For example, in this figure, the state of nitrogen is fixed by two independent intensive properties, the temperature and specific volume. Together, they can fix the state of a simple compressible system. And the simple compressible system is considered if a system involves no electrical, magnetic, gravitational, motion, and surface tension effects. To discuss about process and cycle. Any change that a system undergoes from one equilibrium state to another is called a process, and the series of states through which a system passes during a process is called the path of the process. It is shown in the figure the process between states 1 and 2 and the process path. And to describe a process completely, one should specify the initial and final states of the process as well as the path it follows in the interactions with the surroundings. Now, let's talk about a quasi-static or a quasi-equilibrium process. And this can be viewed as a sufficiently slow process that allows the system to adjust itself internally so that properties in one part of the system do not change any faster than those at other parts. And these are illustrated in the figure. When a gas in a piston cylinder device is compressed suddenly, the molecules near the face of the piston do not have enough time to escape, and they will have to pile up in a small region in front of the piston, thus creating a high pressure region there. Because of this pressure difference, the system can no longer be said to be in equilibrium, and this makes the entire process non-quasi-equilibrium. However, if the piston is moved slowly, the molecules have sufficient time to redistribute and there will be no molecule pile-up in front of the piston. As a result, the pressure inside the cylinder will always be nearly uniform and will rise at the same rate at all locations. Since equilibrium is maintained at all times, this is considered as a quasi-equilibrium process. And it should be pointed out that a quasi-equilibrium process is an idealized process and is not a true representation of an actual process. Process diagrams plotted by employing thermodynamic properties as coordinates are very useful in visualizing the processes. Some common properties that are used as coordinates are temperature, pressure, and volume or specific volume. The figure shows the PV diagram of a compression process of a gas. This is the compression process and this is its PV diagram. Note that the process path indicates a series of equilibrium states through which the system passes during a process and has significance for quasi-equilibrium processes only. For non-quasi-equilibrium processes, we are not able to characterize the entire system by a single state, and thus we cannot speak of a process path for a system as a whole. A non-quasi-equilibrium process is denoted by a dashed line between the initial and final states instead of a solid line. Now, the prefix iso is often used to designate a process for which a particular property remains constant. An isothermal process, for example, is a process during which the temperature remains constant. An isobaric process is a process during which the pressure P remains constant. An isochoric or isometric process is a process during which the specific volume remains constant. A system is said to have undergone a cycle if it returns to its initial state at the end of the process. That is, a cycle means A process during the initial and final states are identical. Steady flow process. The terms steady and uniform are used frequently here. The term steady implies no change with time, and uniform implies no change with location over a specified region. Steady flow process is defined as a process during which a fluid flow through a controlled volume steadily. During a steady flow process, fluid properties within the controlled volume may change with position but not with time. A large number of engineering devices operate for long periods of time under the same conditions, and they are classified as steady flow devices. Examples for this are the turbines, pumps, boilers, condensers, heat exchangers, power plants, and refrigeration systems. Under steady flow conditions, the mass and energy contents of a controlled volume remains constant. Let's discuss now the temperature and the zeroth law of thermodynamics. Although we are familiar with temperature as a measure of hotness or coldness, it is not easy to give an exact definition for it. We express the level of temperature qualitatively with words like freezing cold, cold, warm, hot, and red hot. However, we cannot assign numerical values to temperatures based on our sensations alone. Fortunately, several properties of materials change with temperature in a repeatable and predictable way, and this forms the basis for accurate temperature measurement. The commonly used mercury in glass thermometer, for example, is based on the expansion of mercury with temperature. As shown in the figure, two bodies reaching thermal equilibrium after being brought into contact in an isolated enclosure. The zeroth law of thermodynamics states that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. However, it cannot be concluded from the other laws of thermodynamics, and it serves as a basis for the validity of temperature measurement. By replacing the third body with a thermometer, the zeroth law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading even if they are not in contact. As the name suggests, its value as a fundamental physical principle was recognized more than half a century after the formulation of the first and the second laws of thermodynamics. It was named the zeroth law since it should have preceded the first and the second laws of thermodynamics. Temperature scales enable us to use a common basis for temperature measurements. All temperature scales are based on some easily reproducible states, such as the freezing and boiling points of water, which are also called the ice point and the steam point. A mixture of ice and water that is in equilibrium, with air saturated with vapor at 1 atmospheric pressure, is said to be at the ice point. And a mixture of liquid water and water vapor with no air in equilibrium at 1 atmospheric pressure is said to be at the steam point. The temperature scales used in the SI is in Celsius scale, formerly called the centigrade scale, renamed after the Swedish astronomer A. Celsius, and in the English system today is the Fahrenheit scale, named after the German instrument maker G. Fahrenheit. On the Celsius scale, the ice and the steam points were originally assigned the values of 0 and 100 degrees Celsius. The corresponding values on the Fahrenheit scale are 32 and 212 degrees Fahrenheit. These are often referred to as two-point scales since temperature values are assigned at two different points. In thermodynamics, it is very desirable to have a temperature scale that is independent of the properties of any substance. Such a temperature scale is called a thermodynamic temperature scale, which is developed later in conjunction with the second law of thermodynamics. The The thermodynamic temperature scale in the SI is the Kelvin scale, named after Lord Kelvin, and the lowest temperature on the Kelvin scale is absolute zero or 0 Kelvin, while the thermodynamic temperature scale in the English system is the Rankine scale, named after William Rankine. Take a look at this figure. A constant volume gas thermometer would read negative 273 degrees Celsius at absolute zero pressure. In SI units, the temperature scale Celsius is equivalent to the thermodynamic temperature scale Kelvin, while in English unit, the temperature scale Fahrenheit is equivalent to the thermodynamic temperature scale Rankine. The Kelvin scale is related to the Celsius scale by this equation, and the Rankine scale is related to the Fahrenheit scale by this equation. The temperature scales in the two unit systems are related by this. In this figure, it shows a comparison of temperature scales. So this is for the degrees Celsius and Kelvin. So the equivalent of negative 273.15 degrees Celsius is 0 Kelvin. And for the degrees Fahrenheit and Rankine, the negative 459.67 degrees Fahrenheit is equivalent to the 0 Rankine or the absolute zero. Now let's talk about pressure. Pressure is not what you feel during exams, but pressure in physics is defined as a normal force exerted by a fluid per unit area. It has unit of newtons per square meter, which is called Pascal. We speak of pressure only when we deal with a gas or a liquid. The counterpart of pressure in solids is normal stress. The normal stress or pressure on the feet of a chubby person is much greater than on the feet of a slim person. If the person stands on one foot, then the pressure doubles. If the person gains excessive weight, he or she is likely to encounter foot discomfort because of the increased pressure in the foot. Note that the size of the foot does not change with weight gain. As what you have seen here, the pressure of the slim person has 3 pounds per square inch, and for the chubby person, the pressure is 6 pounds per square inch. So they have same area of the feet, but they have different weights. The pressure unit Pascal is too small for pressures. Therefore, its multiples kilopascal and megapascal are commonly used. And there are other pressure units commonly used, especially in Europe. The bar, the standard atmosphere, and the kilogram force per square centimeter. Note the pressure units of these are almost equivalent to each other. Actual pressure at a given position is called the absolute pressure, and it is measured relative to absolute vacuum, meaning the absolute zero pressure. Most pressure measuring devices, however, are calibrated to read zero in the atmosphere, as shown in the figure. And so, they indicate the difference between the absolute pressure and the local atmospheric pressure. This difference is called the gauge pressure. The gauge pressure can be positive or negative, but pressures below atmospheric pressure are sometimes called vacuum pressures and are measured by vacuum gauges that indicate the difference between the atmospheric and the absolute pressure. The absolute gauge and the vacuum pressures are related to each other by this equation. And we will discuss elaborately about these concepts mentioned as we go along to the next chapters. That is all for today's lecture, and our next topics will discuss about energy, energy transfer, and analysis. Thank you so much for listening and see you soon. Bye-bye.